All right, so today what I want to talk about, this is in many ways a continuation of what we did last week. And like I said, this is like part 2 of like a 3-part series of linear algebra. And today we're going to talk specifically about tensors. Okay. First off, how many people here have worked with tensors or feel comfortable with tensors? Yeah, work with tensors. Okay. So the reason why I ask is because this is usually, I think, the first topic, that most people really haven't seen in graduate level physics, because it's just not something you get exposed to a lot. And so the way to think about this is this is like a general class or generalized objects as compared to vectors and scalars, or even matrices. So the idea is that if you're talking about a scalar is an object where you have, it's just a simple number, okay? So and so we call this a rank 0 tensor, and you'll see why in a minute. So a scalar is just a simple number. A vector is a set of 3 real numbers in 3-dimensional space, and we'll call this a rank 1 tensor. And the matrices that we've seen, they have, let's say, you might have like rows and columns in both. So it's almost like you took a vector and you expanded it out, so it's not just a column, but it also has rows. And so matrices that we've seen are rank 2 tensors. And so the basic idea then is that if you have a vector, say vector AJ, and you contract that vector with the matrix IJ, so we're summing over J, and you have this matrix with this vector, the result is going to be a new vector. And so the question that we run into is, how do we generalize this so that, the nice thing about linear algebra is that it's pretty powerful, as you guys saw. The bad thing about linear algebra is very clumsy, because you got all these terms, and you got to write it out really wide and everything. And so the question is, how do you make it more compact and more consistent? Also, you run into problems because with the matrix, for example, you got matrices and you can have the rows and the columns, but is there an object you can build that goes beyond that? And so, and also, if scalars, vectors, and tensors or matrices are all related, how can they be more unified as one object? And so the tensors are basically something that makes all that work. So here, if this is your transformation matrix, and this is some vectors, okay, then you can think of this Aij as the cosine of the angle between the two coordinate systems. So let's say this is cosine angle between x sub I prime and x sub j. And so what happens is, if you want to transform from x sub j to x sub I prime, then let's say we're going to do this in terms of derivatives, then if you sum the derivative with respect to x sub I prime with respect to x sub ij, and you multiply each one of those terms by dxj, the result should be dxi. And so if you integrate both sides of this, you get the transformation from this vector to that vector, right? And so therefore, we could say that the transformation matrix is just equal to taking the partial derivative of one coordinate with respect to the other coordinate. That's fair to say, right? So we could say then that ai prime is equal to the sum over j of partial xi prime, partial xj, aj. And so what we've done is we basically changed from one vector to the other vector. And so we know that this rule applies for our vectors, and we know we've done this with linear algebra. And so like I said, the whole idea of the tensors is going to be to find a more compact way of saying this. Now you're noticing one thing I've done here without really talking about since last week, is last week I wrote the vectors differently. I would write the vectors as something like this, right? Oh, that sucks. I would write a vector like this. And now I'm writing a vector like this. And the reason why I did that is because, as we talked about last week, and we talked about bases of vectors and components, it became clear that we can pretty much just sum up the vector by the component, right? Because we can kind of switch back from one basis to another. And so if we assume the basis is the same, and we're trying to do our transformation but into the same basis, then we're just transforming the components, which is why we were able to do this. It's a kind of subtle part. Also, the same transformation works for gradients. And so we have that the gradient of a scalar is equal to taking x hat times the derivative of the scalar with respect to x plus y hat times the derivative of the scalar with respect to y plus z hat times the derivative of the scalar with respect to z. So that is meant to be very simple, straightforward, taking the derivative of each component. And so you get from this, then, that if we take, like, say, this del operator, where this is effectively taking the derivative with respect to each component, that taking the derivative of the scalar with respect to x prime I, and I'm going to call this phi prime, is equal to just the same thing as changing the summing over j of partial xj over partial x prime I with partial phi partial xj. In other words, I take my vector, which is essentially formed by taking the gradient of a scalar, and I use this transformation matrix in order to turn it into a new vector, right? But here's one thing that's very, very subtle between these two, is you'll notice that if you look at the transformation matrix here, and you look at the transformation matrix here, the two are opposite of each other. This one has the derivative of x prime I over x prime xj, and this one has xj over x prime I, right? So since the transformation matrices are different, that leads us to say, well, that the vectors are different somehow, right? And so this first one is something we're going to define as a contravariant vector. Yeah.
The phi alone is scalar, right?
Yes.
So I'm going to take the partial derivative of the vector.
It's not just a partial derivative. It's a gradient. Because the gradient operator here, the del operator, has all the vector components built in. So when you take your derivative, you're not just taking a derivative, you're actually taking creating a vector.
I'll look at that the last equation we had.
Oh, right here?
Yeah.
Yeah, well, this is actually a vector as it's written here because it's taking a derivative of a scalar with respect to the vector quantity. And you can see with these components, when you see the I, or the indice, it means it's a vector. Yeah. So anyway, this is a contravariant vector, which is formed because you have the prime above the unprime. And then this is called a covariant vector. Because it's the other way around. And I'm going to go into more detail later on about the difference between contravariant and covariant, but this is just one of those things you need to learn. And
those will always be inverted. Contravariant, inverted will always be covariant.
Mm-hmm. Yeah, contravariant, covariant, they're going to be inverted of each other. So what happens later on is we have this phi prime here, and since phi is a function of x, y, and z, and phi prime is a function of x prime, y prime, and z prime. Since phi prime is a scalar, it's equal to phi. And so what this means is that we can actually turn our phi prime into phi, and so we can actually just call this partial of phi with respect to x prime I equals sum over j of partial x sub j, partial x prime sub I, partial phi, partial x sub j. And so what happens is if you look at this, it's almost like you're just doing multiplication with fractions. And you can see that you have here this term in the denominator and this term in the numerator are the same, right? And so they end up giving you this guy. Where here, you've got the unprimed and the unprimed here. So like these two terms, for example, are the same. And you just work through the math and you see it's the same thing. And so this is the basic idea between contravariant and covariant, where it's just a matter of this transformation matrix. So in Cartesian coordinates, and I want to make this very clear that I'm talking Cartesian, what happens is your partial aj partial x prime I is equal to your partial x prime I partial xj. And those are both equal to your transformation matrix. In other words, contravariant and covariant are the exact same thing in Cartesian coordinates. Which is probably why in your previous classes you've never heard any distinguishing between a contravariant and a covariant vector. But when you start talking about tensors, this becomes a very, very, very important distinction. And the reason why is because when you really start doing stuff with tensors, everything is going to be contravariant or covariant or some combination of the two, and you can never just exchange contravariant and covariant terms unless you know you're always dealing with a Cartesian coordinate system. And so in order to tell the difference, if I write an indice like this is going to be contravariant. And if I write the indice like this, it's going to be covariant. And if I write it with no indice at all, this is called invariant. So the first one is a contravariant vector. The second one is a covariant vector, and the third one is a scalar, because it's invariant. And so when I was in college, somebody was trying to remember what the difference is between contravariant and covariant. So the way I was told was, if you think back to the days of the Super Nintendo and the video game Contra, where you're playing the game and there's like the extra men are always up here on the screen. Then, then you die and you get your extra guy. That was always the contravariant. So, and covariant was the other one. So anyway, so you learn something from video games. All right, so the basic idea then is when you see a tensor or a vector or something like that, you need to know contravariant from covariant. And Cartesian, it doesn't make a difference. Now, where it does make a difference between contravariant and covariant is how it transforms. Like, for example, when you talk about tensors, and so I'm going to talk about rank 2 tensors. And by the way, when I say rank refers to the number of indices you have. So if I have a rank 2 tensor, that means it has 2 indices, the ij. And this rank 2 tensor is going to transform from the unprimed to the prime coordinate system using 2 transformation matrices. And so this is called a contravariant tensor because it has 2 indices and they're up, and you can see it's rank 2 because there's 2 indices, and it needs 2 transformation matrices to transform it. Where with the scalar, or sorry, with the vector, you can see it only needs 1 indice, or 1 transformation matrix to transform it, because it only has 1 indice. With the scalar, it doesn't need any indices. So it has no indices, so it's no transformation matrices. And then you can see that if I had a, I'm going to call this a B, if I had a mixed tensor, then what it is part contravariant, part covariant, and you can see that it's going to have one where it's going to be primed in the numerator, and the other one's going to be primed in the denominator. And you can see that this transforms with 2 indices, but one's up and one's down. And then I could even make a third one where it's 2 lower indices. And you can see again, this needs 2 transformation matrices. Nope. No, the number of indices has nothing to do with the number of dimensions. So what happens is, and that's kind of the beauty of tensors, is that the number of the number of indices denotes rank, and it denotes the number of transformation matrices you need. So if it doesn't need any of these, it's a scalar. If it needs 1, it's a vector. If it needs 2 or more, it's a tensor. But the thing about it is, unlike matrices, I can have more. I don't have to stop at rank 2. Like if you think about it, I could take a rank 2 tensor and I could write it as a matrix, and where each one represents the columns and the other one represents the rows, right? But what about 3? If I try to make that a matrix, it's going to look like a Rubik's Cube. and then we'll go rank 4, and I'm getting like some kind of hypercube. And the map just breaks down, it doesn't work. So, but with tensors, I could have as many rank as I want. I could have a 32 rank tensor if I wanted to, or 154,000 rank tensor. And, and I could and it still works as a consistent mathematical object. The only thing is that to transform it, I need to have one of these per indice. And as far as the number of dimensions go, if K goes from dimension 1 to dimension 3, it's 3-dimensional. But I'm not limited to that. I could make this a 5-dimensional, I could make it a 20-dimensional, I could make it a 2-dimensional. So I can arbitrarily change the dimensionality of my problem anytime I want with tensors, which is part of the big advantage of it, because you can't do that with a matrix. You're stuck with a 3x3 or 4x4 or something like that. And so and this is why we use this in physics, is because I can, if I'm working especially in relativity or in particle physics, I might want to be doing things in terms of 3 dimensions. I might want to do it in terms of 4 dimensions. I might want to do like string theory and have 11 dimensions. Or M theory, add another dimensional to it. And the math holds up with this. So all that really affects is the number of dimensions. So to put it another way, rank equates to the number of indices, which equates to the number of partial derivatives that you need for the transformation. Dimensions is independent of rank. Like I said, and so that's the real selling point on this for physics. And so if you have like a rank 2 tensor, in 3D, then it would look something like a 3x3 matrix. Okay, so we can have tensors of arbitrarily higher rank, but anything that you have higher than second rank, you can't consistently write as a matrix. I mean, you could probably rank, if you have 3 indices, you can possibly write that as a matrix, like where each one is like a column vector put next to each other, but it really gets hard to consistently write anything higher than that. And so when you have a set of numbers, and if they're going to form a tensor, they need to transform like a tensor. And to transform like a tensor basically means that you have to have one transformation matrix for each indice consistently in order for it to transform to a new coordinate system. So if you alter your coordinate system, you can transform your tensor to work with the new system. Any questions so far? This is the basics before we really get into the math of it.
What's the difference between a tensor and a differential form?
We can get to that a little later. But I think that's a little more complicated. All right, so when we talk about tensors, we've got different properties like addition and subtraction, where they're just like matrices in that you can literally add together each term by term and get, a new tensor. And so they're just like, you just add element by element. And you'll notice here that in order for this to work, A and B have to have the same rank and the same number of dimensions. All right. Also, what happens a lot is that we have this thing called the Einstein summation convention, where what that means is that we don't like having to write these summation signs everywhere, like here and here, because it just becomes kind of redundant after a while, and we're lazy. So what they come up with is called the Einstein summation convention, which we're going to use. And what that means is that if you have an indice and you repeat that indice, contravariant, covariant, then that implies a summation over the indice. In other words, you can write your transformation for that mixed tensor like this, like partial I prime with respect to xk, partial xl, partial x prime j, and then bkl. And you can see that the k is repeated between the b and then this first term, and the l is repeated between here and here. And since this one is considered contravariant, this is considered covariant. This is considered contravariant, that's considered covariant. And so because we're repeating those indices, then it just implies a summation instead of actually having to write it out. We also have a Kronecker delta, which by definition is like partial x of I, partial x of j. And so you could see that if x is the same dimension, this is going to give you 1. If these are different, these are going to give you 0. So if this is y and this is x, that's 0. But if this is x and x is 1. And you'll notice here that your Kronecker delta can be written like partial xi prime, partial xk, partial xl, partial x prime j, delta kl. So your Kronecker delta can be a tensor which transforms into the new coordinate system, but it's still basically the same thing. It's just it's now going to be defined in terms of derivatives of the prime coordinate.
Are we doing contractions and stuff? Does the order of the indices matter?
Yes. Well, I mean, it matters in some cases. If you have it like this, where you can actually exchange the indice order, then this is called symmetric. And so it's literally the same thing as when you transpose a matrix. If you had something like this, then this is anti-symmetric. And so what typically happens is you get something that's neither symmetric nor anti-symmetric, and and that doesn't matter. But what happens is if I contract, say, BI, AI, this is equivalent to AI, BI. It doesn't matter what order I put those in. So here, order is not important. And by the way, this is actually the definition of a dot product. Two vectors. And so also you can have any one of these guys as both symmetric and anti-symmetric parts. So you can write the symmetric part by just simply taking the tensor and reversing the order on it, and multiplying by 1/2, and then what comes out of here is automatically symmetric. And in to get the anti-symmetric part, you would actually take your tensor and you'd subtract out the 1 with the indices flipped. And so this is the anti-symmetric part, and this is the symmetric part. And you can see, do a little simple math, you can see that this just adds up to the same thing. And so this comes in handy because sometimes you actually want to deal with symmetric only terms. Sometimes you want to deal with only anti-symmetric terms. And so this gives you a way of symmetrizing or anti-symmetrizing your tensors. And also the beauty of one other nice thing about this is that we can actually do the math without actually caring what's inside the tensor. So it's not like linear algebra where you have to populate your matrices with a bunch of numbers in order to figure out how to take a determinant. This you can actually do just algebraically. Now also another thing that we're not going to talk about today are called spinors. And these are just a fourth mathematical object. They're not really scalars, vectors, or tensors. And essentially what they are is they're like complex sets of numbers, and they're used to describe fermions and other particles in group theory and particle physics. But we're not going to really go into those here. So I think we mentioned contractions earlier. And this dot product here is an example of a contraction where you literally take two vectors and turn them into one scalar. Because you're contracting over all the indices. And the neat thing about a contraction is that it literally is an operation which reduces the number of indices by 2. And so you can almost think about it as these two eliminate each other and you're down to 0. And another example could be, let's say you have B prime I. So this is our mixed tensor from before, and it's basically a transformation matrix and it's acting on our mixed tensor. And so what happens is you notice that these two are the same. So I take this term in the numerator and this term in the denominator. They're the same. And so this is equivalent to partial XL, partial XK, acting on BLK. And now this actually looks like a Kronecker delta. And so now by definition, the Kronecker delta turns this into a BKK, which is a scalar, because they're the same indice. So we could just call this something like B. And so what we learned from that is that the scalar really is the same in all the different dimensions, all the different coordinate systems. So here you take a scalar, or sorry, take a tensor, and you contract over its two indices, so it becomes a scalar, and you see that it doesn't transform. Now we also have this thing called a direct product. A direct product is where you actually might have something like two different vectors, like a contravariant covariant vector, and they combine to give you a new tensor, where you could see that these I and J are different, and it results in a new mixed tensor. So A prime I, B prime J is equal to taking the transformation matrix, AK, and then the transformation matrix, oops, I forgot this is supposed to be primed here, and then another transformation matrix, acting on BL. And so if you can take these now and you can move these around anywhere you want. And this is one of the nice things about tensors, is that unlike with matrices where we have to keep writing everything in a certain order, here we can mix up the order. So we have the two transformation matrices we could write first. And you have AK, BL. And so this part right here, the first part with the derivatives, that is literally the transformation tensors, and this part is like the tensor. So it's like a mixed tensor. So we could say that just taking two completely different tensors and putting them next to each other, we can create a new tensor. And so an example of that, again, is if that AIJ contracted with BKL, that could form a new tensor, and I could call that tensor CIJKL. Yeah, that's totally legit. So I could just redefine tensors however I want. Okay. All right, any questions so far? Okay. All right, so next up, let's talk about pseudotensors. Now, a pseudotensor is essentially, it's kind of like a tensor, but it doesn't transform exactly like a tensor. An example here is, let's suppose we have a transformation matrix, which is like a negative delta function. In other words, everywhere it has x of I, it turns it into minus x of I by just inverting, inverting everything. And so if you have a coordinate system, let's say we have x1, x2, and x3. And within this coordinate system we have some vector r. Then under this type of transformation, we're going to still have a vector r, which is going to be pointing like this, but everything else is going to be inverted. So x2 is going to be pointing down. x1 is going to be pointing this way, and x3 is going to be pointing, instead of out that way, it's going to be pointing this way. Okay, and so you can see that everything has changed, all the coordinates have changed, but the vector is really the same old vector. And so this is r prime now. And so what's happened is that most coordinates, or most vectors, are called polar vectors. Where a polar vector is one where the sign of the vector is reversed when you apply this type of transformation. In other words, it's called odd parity.
So what exactly happens with the farm that flipped?
Yeah, because if you think about it, let's suppose R was just pointing along the x direction, right? And then we flipped all the coordinates. Now R is pointing along the negative x direction, right? And so we could say that, well, the value of R has flipped because of the flip in the coordinate system. And that's normal odd parity. That's what you expect to happen. And so that's the definition of a polar coordinate. What happens with a pseudo-vector is a pseudo-vector we're going to see is something where you have even parity, where the exact opposite happens. Like where you flip the coordinates and the sign of the vector stays the same. An example of that is if you have two polar vectors, let's say A and B, and you have a new vector C, which is formed by a cross product of vector A and vector B, then you can write that as CK is equal to AI BJ minus AJ BI, where I is not equal to J and it's not equal to K. And so if you have AI and it turns into minus AI prime, and you have BJ and it turns into let's see. Sorry, I should be consistent, where these are all contravariant. So you have BJ turns into minus B prime J. Then you could see that because you have minus signs everywhere, that CK is going to turn into plus CK prime. So this is a way of constructing this in a way that you have no change in the vector, even though you flip the sign of everything. And so this pseudo vector has even parity. Which means that even though you flip, and also, it's also known as an axial vector in some places. So now, let's suppose, well, let's look at some examples of this. One example is angular velocity, where angular velocity comes from the cross product of angular, velocity comes from a cross product of angular velocity and the radial vector. Or angular momentum, like orbital angular momentum, that comes from a cross product of the radial vector and momentum. We've got torque, which comes from essentially force and the radial vector. And you've got magnetic field, where a magnetic field, you get Maxwell's equation. A time derivative of magnetic field is equal to taking minus the curl of the electric field. And so each one of these pseudo vectors is essentially comes from taking the cross product of a polar vector or two polar vectors. And so the idea then is that you could have also what we call a pseudo-scalar, where a pseudo-scalar is where you might have something like S prime transforms into the determinant of A times S. A pseudo-vector transforms as taking your vector where you have the transformation involves a determinant of your transformation matrix and then your transformation matrix. And in a pseudo tensor, it is the same thing. So you have A prime ij has the determinant of A, and you have two transformation matrices. And so in each one of these cases, you can see you have to have the determinant of A to make it work. And so under inversion, you have that your transformation matrix is equal to -1, -1, -1. All the rest are zeros. And the determinant of A is equal to -1. And that is why a pseudo-scalar is, or any of the other ones, are going to flip sign when you change the coordinate system. But if you have a reflection, then your transformation matrix is going to essentially be -1, 1, 1, because essentially you're just taking one dimension and you're flipping it. And you can think about it like when you look in a mirror. You know, everything is the same as far as height and width, but the in and out part, it just kind of flips that around. And so in here, the determinant of A is also equal to -1. But if you did a rotation, where you have like 0, 0, 1, 1, 1, then here the determinant is equal to 1. So a pseudo-vector or pseudo-scalar, under rotation, they won't flip sign. Okay. All right, everybody good? Like I said, I know this is some new stuff. Okay. Let's see. Next thing I want to talk about is a very special object. And this is not a tensor, but it looks like a tensor. It's called a Levi-Civita. And it's written as epsilon, like ijk. And this is known as an anti-symmetric symbol. It is not a tensor. And the reason why it's not a tensor is because it does not transform like a tensor. This thing has the magical property that it is completely anti-symmetric and has 3 indices. And what that means is if you have epsilon 1, 2, 3, or epsilon 2, 3, 1, or epsilon 3, 1, 2, they're all equal to 1. And the idea here is that if I if I had epsilon 2, 1, 3, or epsilon 1, 3, 2, or epsilon 3, 2, 1, these are all equal to -1. And so what happens here is that if you flip the order of the indices just one time, you flip the sign. But if you flip it twice, you flip the sign back. So if I flip the order of 3 and 1, that flips the sign to -1. But if I flip the order of 3 and 1 and then flip 1 and 2, that gets it back to 1. Does that make sense? And everything else, like if I had epsilon 2, 2, 1, or epsilon 3, 1, 1, or something like that, all of those are equal to 0. And the reason why is because if you repeat an indice, you're already saying that, if you flip it, the order of those two indices that are repeated, it has to be the same, it has to be minus itself, and the only thing that could be negative of itself is 0. So this thing has 3 values, 1, -1, and 0 for each component. Okay, does it make sense? All right, so that basically means, and I could write this as epsilon I to show. So this is a pseudo tensor. And the neat thing about it, and this is like one of the first problems I saw when I got into grad school, was epsilon ijk. Since it's a pseudo tensor, this is the determinant of A, and then you have the transformation matrices. Sorry, I meant Q, not row. So this is a pseudo tensor, but the neat thing about the pseudo tensor is that you can actually use this to just define the operation of calculating a determinant in using tensor form. So because it's a pseudo tensor, it actually allows you to, it gives you a way of calculating a determinant, and also because you know what it is. It also is useful for cross products, because you can actually write A cross B equals C in terms of tensors by using this thing, because you can have Ci equals epsilon ijk ajbk. So this is also a very, very, very useful thing, because you can, you could use it to define determinants. You could use it to define cross products. All right. This brings us to the idea of dual tensors. And a dual tensor basically comes from the idea that now that you have this Levi-Civita symbol, if you take the right tensors, you can kind of do some really interesting stuff with it. Here, I've got this C term here is an anti-symmetric. This is an anti-symmetric tensor. This is, of course, Levi-Civita. And so what happens is, because this is anti-symmetric, and the Levi-Civita is anti-symmetric, that you can actually pull out this thing called a dual pseudo-tensor from it, which looks a lot like a vector. Or so it's a dual pseudo-vector. And the neat thing is that this vector will contain all the information of this tensor, but in a much more compact way that we can work with. And so let me show you how to...
What's the exponent of the tensor there? Is that JK?
Oh yeah, JK.
Okay.
Sorry. Make that a little bit more clear. All right, so what we can do is, for example, let's say that tensor, we'll write it out as a terms of matrices. So it's anti-symmetric, so you got minus Cij, or C12, C31, minus C23, zeros down the diagonal, and then this is going to be C12, this is going to be minus C31, and this is going to be C23. Okay, so what happens is when you take this and you apply the Levi-Civita, the vector that comes out is actually going to look like C1, C2, C3, and it's going to be composed simply of C23, C31, C12, because it's going to have all the same elements. And so what happens is when you multiply this tensor by the pseudo vector, what you're going to see is you're going to have either 1 or minus 1 come up for each one of these terms. And so you'll have like a 1 times C23, and you're going to have a minus 1 times minus C23. They add together to give you the same thing. And the result is that, you know, there's really only 3 unique components in this tensor, so that gives you the 3 components for the vector. And so we call this duality because your 3D pseudo vector is equivalent to an anti-symmetric rank 2 tensor, which seems odd that you could have something of a lower rank that is exactly equivalent to something more sophisticated. Another example is that let's say we do a direct product of vectors. So Vijk is really equal to 3 vectors A, B, and C. And so this pseudo-scalar can be written as 1 over 3 factorial times epsilon ijk acting on Vijk. So this is a rank 3 tensor, and this is a pseudo-scalar. And so here, V, you could say it's equal to A1, A2, A3, B1, B2, B3, and C1, C2, C3. And so V is equal to the determinant of V, effectively. So this pseudo-scalar is effectively taking the determinant of this matrix formed by combining these vectors as a direct product. And so that means that, you know, all that information is just kind of compact. And so this leads us to the idea of reducible tensors. And the basic idea is that if you take, you could take a tensor and it could be rewritten as the sum of rank 0, 1, and 2 irreducible tensors. So, for example, we might have Bij, which is equal to 1/2 of A Ij minus A Ji. So in other words, we have A Ij, which is neither symmetric nor anti-symmetric, and we've made it anti-symmetric. So this is anti-symmetric. And because it's anti-symmetric, we can actually write a pseudo vector where we're going to use the Levi-Civita symbol. With this. And so this is a pseudo vector. And so also we can create a symmetric tensor as well by just simply, instead of subtracting, adding together the Aij's. And so this is a symmetric tensor. And then we can actually subtract out the trace of that. So if we take Sij and we subtract out 1/3 A with a delta Ij, then this we're going to call it S prime Ij. So this is the trace-free. And so what this means then is the trace-free part, you can see that this is just a scalar that comes from, you know, taking the determinant of whatever this is, or the trace of A by itself. And so therefore, we could say that our tensor A can be written as 1/3 of this scalar term plus a pseudo vector plus a trace-free part of the symmetric term. So this is rank 0, this is rank 1, and this is rank 2. And so we've reduced our tensor down to its basic components. All right. Any questions?
All right. So they're using when they're doing like compression, I mean, you can use the compression algorithm and stuff.
Yeah. Actually, they use a lot of tensors for that. So if you're talking about stress and strain, and yeah. And that's the thing. It's like I use it a lot in general relativity, and actually a student a few years ago, he was interested in trying to put a connection between that and what you see in like stress algorithms, like mechanical stress, because in there you're constantly flipping through dimensions the same way. It's just a little bit, you know, different how it's used. All right. What I'd like to do right now is just take a quick break, and then we can get on with the metric, because it's going to be next, which I want you guys to be fresh for. What?
Just defining a metric.
We're going to be using metric.
Well, then you're going to be doing all the.
Yeah, we're going to be using metric. So the next thing I want to talk about is the metric. And so the metric is the most important tensor. And what it ends up leading to is, I mentioned it before, but it actually ends up leading us into differential geometry. And if you ever move on and study general relativity or a lot of more advanced topics in theoretical physics, then this is something that you're definitely going to be running into. And so the basic idea here is if you start with a transformation, where you go from a generalized coordinate q to a new coordinate x, then what happens is their differentials are always going to be linear. So dx is always going to be equal to partial of x with respect to q dq. All right, and another way of writing this is you could say that the vector dx is equal to some other vector, I'm going to call it epsilon, of dqj, where this epsilon is equivalent, to just taking the derivative of the vector with respect to the generalized coordinates. And so this is basically just some kind of set that is formed by that transformation. Now notice that this is the basis, but it's not necessarily a unit vector. And so the unit vector, e hat I, is really equal to 1 over hi times this epsilon. Where this hi is the one that we talked about last week. And so this epsilon is equivalent to taking hi times e hat I, where the hat terms are the unit basis. The epsilon is the full basis. And so in spherical coordinates, epsilon r is basically just e hat r, which is equal to r hat. Epsilon theta is equal to r e hat theta, which is equal to r theta hat. And epsilon phi is equal to r sine theta of epsilon hat phi, which is equal to r sine theta phi hat. So that should all look very familiar to you. And so what happens is that our transformations are such that if you have a contravariant vector, then that's the transformation matrix multiplied by your vector. And so we can rewrite that as saying that v prime is equal to vj times epsilon j. So the epsilon j is the basis, and then the vj is the component. And so this is a contravariant vector. And so what I'm going to do, and since we're going to get into a lot of derivatives here, is I'm going to use some shorthand. One of them is going to be, if I write partial I like this, this is going to imply that I'm taking a derivative with respect to xi. And then And that is going to be equal to if I take a derivative of coordinate with respect to xi, and then I multiply that by a derivative with respect to the coordinate. And so in doing that, when I make this statement, partial I, I'm not really referring to the coordinate system. So this is a coordinate independent thing. Okay? So let's see. And so in a lot of ways, this is like the inverse of the transformation equation. Now you also notice that if I took v prime I subscript, and I wrote that as partial qj partial xi of vj, that is equal to, or equivalent to, v I, or v prime equal to vj epsilon j, where this is covariant. So you notice a covariant vector has got a basis where the indice is up and the component is down, where the contravariant, the indice on the component is up and the basis is down. That's the big difference between the two. See, I didn't actually need this. All right, so when we have a second-rank tensor, then we'll just define that like we did before. A prime ij is going to be formed by epsilon I think I got the car that headed up yours. Yeah, actually, I got it right. So yeah, you can think of the PHYS as being equal to epsilon I epsilon j times a all right, I think I got that wrong. Whoops. Yeah, I did. I got a little bit ahead of myself on that one. Well, this is still the same thing where it's like partial x I partial q k with partial x j partial q l a k l. Now, this leads us to differential displacement. And the differential displacement is basically ds squared is equal to taking dr and you're dotting it with itself, which is equal to taking epsilon I dq I and squaring it. So it's equal to just taking epsilon I epsilon j times dq I dq j. Now, if you take epsilon I times epsilon j, that is equal to Gij, the metric. And you can see that that falls from before when we defined epsilon I as being hi times this unit vector term. And so h squared will give you the Gij terms. And so this is called the contravariant metric tensor, or just the metric tensor, or the metric, or however you want to define it. But the thing that comes out of this is that the metric is definitely symmetric. Because if it wasn't, you know, putting these things in the opposite order would actually mean something. Now also you'll notice that we have this thing, we can have an inverse metric. We have Gik, Gkj is going to give us a delta Ij. And that's going to be true because effectively we're just going to have, let's say, vector V is equal to epsilon j times epsilon j superscript times V. So because this is true, that it gets you back to V, then having an inverse metric with a metric is going to give you that. And the inverse metric is basically saying that you're going to take these two indices on the epsilon terms and you're going to raise them up. So this first term here is the inverse of Gkj. The inverse metric, one thing we're going to use it for is going to raise indices. It has the magical power that it can turn a contravariant vector into a covariant vector, or sorry, a covariant vector into a contravariant vector, where the metric lowers indices. It can turn a contravariant vector into a covariant vector. And so every time, and so what we're going to do is anytime you're doing your math with tensors and you need to lower an indice, you use the metrics. And see, here's the beautiful thing about it. For the Cartesian coordinates, the metric is just ones down the diagonal. And the inverse metric is just ones down the diagonal. Right? So when you multiply any vector by that, it's unchanged because it's basically, it's the identity matrix. And that's why it is that in Cartesian coordinates, there's no difference between contravariant and covariant, because the metrics are just identity matrices. But when you get to spherical coordinates, or something like that, now you multiply something by the metric, and now it actually changes something. And so what happens is we can see this is if I have, for example, epsilon j, and I multiply it by a Gij inverse metric. The result is going to be this. If I have a vector f, and I multiply it by the inverse metric, the result is going to be the contravariant form of that vector. And then I can do the same thing to lower it. Like if this is epsilon j, I have an ij here. This becomes epsilon I. If I have Gij acting on the contravariant, then it becomes covariant. Oops. So this is one of the neat things about it. Now if we look at this in spherical coordinates, then what happens is the metric actually looks like this, where it's actually like 1 r squared and r squared sine theta. And the inverse metric looks like 1 over r squared and 1 over r squared sine theta, squared theta. Sorry, yeah, just sine squared theta. So you can see here that multiplying something by the metric is going to make a difference. Like I said before, the only reason why you never noticed this before was because you're always working in Cartesian coordinates. Oh no, that's just G. Yeah, it's probably just my pen moves a little fast. All right, so this is the basic idea of the metric. Now, next thing I want to talk about is how do we use it, and how does it come into play? And the answer is basically that the metric changes depending on what your coordinate system is. So as you alter your coordinate system, you're going to get a different metric, and then by having a different metric, then that's when your contravariant and your covariant are going to be different, right? And so this brings about the question, well, if I take a derivative like a gradient in spherical coordinates, I get a different answer than if I take a gradient in Cartesian coordinates, right? So how does the metric play into that difference? And so that's what I want to talk about next. And the answer is going to come down to something called Christoffel symbols. And this is another thing that it's going to look like a tensor, but it's really not a tensor. I mean, unlike the Levi-Civita symbol, these are not even pseudo-tensors. So the idea here, and yeah, the idea here is that if I take the derivative of a scalar, then that is equal to taking the partial derivative of the scalar with respect to some coordinate times d of that coordinate, right? So what happens is that this term right here is a contravariant vector. So therefore, this right here has to be covariant. And so we're automatically, it's like we're creating and then destroying vectors when we're doing this, simple things. And so we could say that if you take the gradient of a scalar, then that is like saying partial psi respect to q I is equal to, times epsilon I is by definition the gradient. And so the divergence, I'm sorry, I'm getting ahead of myself again. So when you take the derivative of a vector, this is like saying partial respect to qj of v prime k. So I'm taking the derivative of my vector. This is like, and so now I'm taking the derivative of this vector. You can see it's primed, so I have to change it to the unprimed frame, right? And that's the transformation I need to do in order to change. Actually, I got too many K's. Actually, this should be an I. By the way, one rule of the Einstein summation rule is that you never want to have the same indice repeated more than twice, because then it's kind of hard to figure out what you contract with what. So now in this case, what this does now is this transforms from the unprimed to the prime frame, and then I take a derivative of it, right? So now, because I got the derivative of this thing, that means that I have to take a derivative of this and then the derivative of the transformation. So I have to do a chain rule thing. So I've got partial xk, partial qi, and partial vi, partial qj, because I applied the chain rule to this. And then I've got another term where I'm taking the second derivative with respect to the x term, and now I'm taking a derivative with respect to qj and with respect to qi of that, multiplied by vi. All right, so this is actually equivalent to taking partial vi, partial qj of epsilon I plus vi times the derivative of this, which is actually derivative of epsilon I with respect to qj. Okay? So this first part right here looks like just a derivative, where it looks like all I did really was take the derivative of the, in order to take the derivative of this primed vector, I've got the derivative of the unprimed and then a transformational. And this right here is just like an extra term, which seems to only come from how my coordinate system changes with respect to this particular coordinate. Because after all, if epsilon I is a constant, that term goes away. And if I'm talking about Cartesian coordinates, it's a constant, that's no problem. But if I'm talking about spherical coordinates or cylindrical coordinates or anything else, that term is non-zero, and I got a problem, right? So this term we got to figure out what to do with. And so what I'm going to introduce is the Christoffel symbol, which is that this term is by definition the Christoffel symbol, which is this capital gamma multiplied by epsilon k. And that's going to be the definition of it, so that the Christoffel symbol is equal to epsilon m times, where this is an m and that's an m, of partial epsilon I with respect to qj. So this is the definition of the Christoffel symbol, and so it's basically a second kind of correction coefficient. And I'll go a little bit further into why it's a correction coefficient. But the idea then is that because epsilon is a constant in Cartesian coordinates, then in Cartesian coordinates, the Christoffel symbol is just going to go to 0. And so you can see here that by taking the derivative of the epsilon terms, this is like second derivative of r with respect to both q, I, and qj. And so that is equal to taking the epsilon with respect to I dq j. And so you can see that this, either way you slice it, you're going to end up with something the same way. So those two are equivalent. And so therefore, the Christoffel symbol ij is equal to the same thing with a ji. And what you'll often see in literature is that the Christoffel symbol would be written like this. And what that is that it's basically taking the metric term and contracting it with the Christoffel symbol. Oops. And so this is called a Christoffel symbol of the first kind. Sorry, it should be 2 F's and 1 L. As opposed to these other ones, like this, these are Christoffel symbols of the second kind. So this gamma ij comma k is equal to gmk times epsilon m dotted with partial epsilon I respect to qj. And so what happens is, when I write it out like this, you can see that all this metric is doing is lowering the indice here. So this is going to be epsilon k times partial epsilon I partial qj. And so when you look at the derivative of the metric, let's say you take the derivative metric with respect to your coordinate, this is equivalent to saying, well, I have the partial. Basically, it's like saying taking the derivative of this thing here. So it's like I have partial epsilon I with respect to qk dotted with epsilon j plus epsilon I times partial epsilon j with respect to qk. And that just comes from the chain rule and the definition of the metric. And so if you compare this to what's above, you could see that that is just simply equal to taking gamma ik comma j and adding to that gamma jk comma I. So there's a clear relationship here between the metric, or at least derivatives of the metric, and the Christoffel symbol. right? And so if you do a little bit of algebra with this, what you can find is that the Christoffel symbol is equal to taking 1/2 times, and I'm going to use some shorthand here, G, I, K, comma, J. And what that means is that G, I, K, comma, J is equal to taking the derivative of the metric with respect to QK for QJ. And so I have this plus G JK comma I minus G IJ comma K. And that'll actually get you the Christoffel symbol. And you'll notice that if you took each one of these terms and you filled in what we have here, that we can show that this is true. And so in general, you could say, well, that gamma S IJ is equal to just taking GKS times gamma IJ comma K, and that is equal to 1/2 GKS times GIK comma J plus GJK comma I minus GIK or IJ comma K. So in other words, you can form this Christoffel symbol, which, like I said before, is just a correction on the derivative term by just simply using the metric and derivatives of the metric. So the Christoffel symbol is basically just a product of how the coordinate system varies. And where this comes in handy is in the covariant derivative. All right, so the idea here is if you take the derivative of a vector, this, from what I had before, is equivalent to taking the derivative of the vector that you would have in the unprimed frame multiplied by the epsilon term, where the epsilon term is basically how the coordinate system is different. And then adding to that the vector times the Christoffel symbol times this change term. And so what we can do is that because we're contracting over k here, we can switch the i's and the k's around, which is legal to do in tensors. And we have partial vi partial qj plus vk gamma I kj, and then the whole thing multiplied by epsilon I. And so what we do is we write this in shorthand as v prime I semicolon j, where the semicolon means that you've taken, we call a covariant derivative. A covariant derivative is a derivative beyond a partial derivative in that it actually respects the coordinate system that you're taking the derivative in. And so this is equal to partial VI partial QJ plus VK times gamma I KJ. And so this is our covariant derivative. All right, and so in this case, VI semicolon J is the jth component of a second rank tensor. And so you'll notice in Cartesian coordinates, this Christoffel symbol disappears. And what happens is the partial derivative is the covariant derivative, and it's the same thing. And so we would write that as in Cartesian, we would have partial V prime I partial Q J is equal to VI prime comma J, which is equal to V I semicolon J. It says I don't even need those primes. So the difference here is that covariant derivatives depend on the curvature of the surface, while partial derivatives do not. And so one way of saying this thing is that a covariant derivative actually carries the laws of physics with it, unlike a partial derivative. And this is illustrated, this is not in your book, but this is best illustrated in an idea called parallel transport. The basic idea here is that let's suppose we have a globe, okay? And at the globe, we take a derivative here at the equator. Now, if I take this derivative at the equator and I move it around the equator and I bring it back here, it looks the exact same, right? But what if I take the derivative, this arrow, and I move it up the globe to the North Pole? And then I move it back down along the line of latitude. Is it pointing in the same direction? Is it? No. Yeah, because I mean, if you think about it, when it gets to the North Pole, it's going to be pointing into the board. And then it comes back down here, it's going to be pointing in. So that's a problem that you run into in geometry, where you need to be able to respect the shape and the geometry of your problem in order to do things correctly. And that's where the covariant derivative comes in, is it actually has kind of, it's pre-programmed to respect the shape of the globe or whatever your coordinate system is. And so what we do is, like, every time you make a move in this globe, in this case, the Christoffel symbol kicks in and it makes a little correction. It makes another little correction. It makes another correction. So that when you after you parallel transport this thing up around in any path, when you get back to where you started, it's going to look the exact same. Okay, does that make sense? So that's what it's for, anyway. All right, so this brings us to the idea of the geodesic. Now, some of the stuff you guys are seeing today, this is like beginning relativity, or general relativity stuff. So the idea here is a geodesic is the curve of shortest length between 2 points. And so in Euclidean space, it's just a straight line. But what this is going to do, this geodesic, is it's going to kind of prove that we're taking the shortest distance between 2 points. Now, on a flat table, shortest distance between 2 points is a straight line. What if you're trying to sail around the world? Yeah, then you make a big arc, right? Yeah, because you have to stay on the surface of the Earth. You can't really, barrel through and go straight through the ocean. So the way we see that is that we have ds, which is basically our measurement of length between points. And so if we take the delta of that, where it's integrated, and we set it to 0, this is going to give us the shortest distance possible. And so ds squared is equal to gij times dqi dqj. And so the delta of ds squared is equal to 2 ds delta ds. And that is equal to dqi dqj times delta gij, because I'm doing like a chain rule thing here, plus gij dqi delta dqj plus gij dqj delta dqi. All right? So this is the delta ds squared. Now, the delta of ds should be equal to 1/2 times essentially everything here divided by the 2ds. So it's going to be 1/2 times the integral of dqi over ds times dqj over ds times the delta gij plus gij times dqi over ds times the derivative of delta dqj plus gij dqj over ds and ds of delta dqi, all multiplied by ds, and all that should come out to 0 if I do it right. So delta gij is equal to partial gij partial qk. And then there's a delta qk. This, by definition, is partial k of gij and times delta qk, right? And so basically what I did here was I said that the delta in the metric is the same thing as just taking the derivative of the metric times, a delta in the qk, because it gives us the metric depends on the coordinate. So I can use that to fix the first term. And So I'm going to do integration by parts, your old friend. And this leads to 1/2 times the integral of dqi ds times dqj ds times partial kqij minus d ds of gij, or sorry, ik of dqi ds plus gkj dqj ds. Now all of this is multiplied by delta qk ds, and it should be equal to 0. And so that's after doing integration by parts in order to get these. That's why the derivative of the metric is inside here. So now if we look at this part by part, we have the derivative of gik with respect to ds is the same thing as taking the derivative of the metric and then multiplying that by the derivative of the coordinate with respect to ds. And so you could do the same thing with the other metric term as well. So I can just fill that in just so we don't get the indices mixed up. So what we have now is 1/2 dqi ds times dqj ds times a derivative with respect of the metric minus another derivative of the metric. This would be j, minus another derivative of the metric minus gik of the second derivative of q with respect to s squared equals 0. And so this just comes from all the stuff that was inside of that integral. And the idea being that if the stuff inside the integral is equal to 0, then the integral is equal to 0. Because we don't necessarily know that the delta q is going to be 0. We actually expect it won't be. So all of this stuff in the parentheses here, this is just a, it's just a Christoffel symbol. And this right here is a second derivative term. So this reduces to saying the second derivative of your coordinate with respect to s plus the derivative of your coordinate with respect to s times the derivative of your other coordinate with respect to s times your Christoffel symbol is equal to 0. And this is the geodesic equation. It's actually, in some ways, it's like half of Einstein's general theory of relativity. And basically, if you take s here and you change it to time, then what this says in physics is that you've got an acceleration in Cartesian coordinates. Acceleration is equal to 0 in the absence of an external force. If you put in spherical coordinates, then this gives you the acceleration of gravity around the Earth or some other object. Where you can see that spherical coordinates means that this is non-zero, and that's where that falls in. And each one of these terms would be like velocity in that case, because it'd be the derivative of the coordinate with respect to time, and this is acceleration. So the second derivative, of course, with respect to time. So in other words, it's a really interesting way of saying that if you take an object in space and it's just empty space, it won't accelerate, but if you put it in a curved geometry, it'll naturally accelerate. Interesting, because it's like basically physics just popping right at us. A bunch of math. So another thing is if we look at dk dqk ds. This is a scalar quantity located on the geodesic. So this is basically some vector dotted with some velocity. And so let's say we take the derivative of this. This is equal to dvk ds times dqk ds plus vk times the second derivative of qk with respect to s. And so that gives you partial vk partial q I dq I ds dq k ds minus vk times the Christoffel symbol dq I ds dq j ds, where I basically took advantage of our geodesic equation in order to expand out the second term. Then you'll notice that we have the velocity terms in both of these. So we may have to just do a change of variables, and we could see that this is just dq I ds dq k ds times partial vk partial qi minus Christoffel symbol ik LVL. And so this right here is just a covariant derivative. So we have this is just basically saying that the change in this vector or the scalar quantity is the velocity squared times the covariant derivative of the vector. All right. So next thing I think this takes us to is just the last couple things where I want to show you how this applies to some things you might be familiar with. The first one is divergence. So I talked a lot, but what does a divergence look like? Now, the divergence is basically taking the dot product of your del operator and some vector, right? And so this is literally going to be just taking your covariant derivative, which is the same thing as taking partial VI with respect to Q I plus VK Christoffel symbol IK. And so the Christoffel symbol IK can be simplified because it is going to reduce down to this. Because you're repeating indices, and you'll notice that if you take the partial of the determinant of the metric, that this is equal to taking the determinant of the metric times GIM times GIM comma K. So therefore, this is looking a lot like taking a determinant of the metric. So you could say that that this Christoffel symbol is just like 1 over 2 times the determinant of the metric, and then a partial of the determinant of the metric with respect to your coordinate. And so your divergence is just equal to VI semicolon I, which is equal to 1 over the determinant of the metric times the derivative of the determinant of the metric, or square root of the determinant of the metric, times VK. So, in other words, you can basically just use the determinant of your metric in order to calculate your divergence. Your Laplacian is basically where, let's suppose you had your vector from before is just the gradient. So you have your gradient, and then you're just raising the indice on it. Then your Laplacian is just taking the divergence of that, and so that becomes 1 over the square root of the determinant of your metric times your derivative of your square root of the determinant of your metric times the metric term with your derivative. And so this gives you kind of a shortcut for trying to figure out what these things are. And you could see that if you have, like say, GII is written as 1 over h squared, using hi squared, using the orthogonal values, then your Laplacian is going to be like 1 over h1, h2, h3 times the partial of h1, h2, h3 over hi squared. times this partial psi, partial qi. Exactly like we had last week. Meanwhile, your curl is where you're taking your derivatives and so that's the curl of v in the k direction. Then you could see that you could write this as vi, maybe it's a covariant derivative, right? And so you would take your covariant derivatives and you'd have your partial derivative term. And then from that, you'd subtract off your other term. And then you could see here that these two extra terms here and here cancel out, and you're just left with vi comma j minus vj comma I, which is exactly what your non-tensor version of your curl is. So the curl is still the curl, and it doesn't really care what your coordinate system is. But you can see that Laplacians and divergences are going to be different, and everything here makes sense from what we had before. All right, so I know that was a ton of information. So any questions you have?
Do you have a formal definition of what a tensor is?
The formal definition of a tensor, I have to look for the exact words, but basically it is a mathematical object that transforms like a tensor. In other words,
Yeah, but you have a formal definition of
Yeah.
tensor, not a.
yeah. I have to think about a better
I
definition.
can't find it in my books.
Yeah, yeah. I don't think I've actually. Yeah, I don't think I've actually read a really good definition that just says this is the best formal definition of it.
Yeah.
I mean, because the thing is, like, a scalar can be a tensor,
Sure.
but it's just a rank 0 tensor.
Yeah.
So it's a very broad thing.
Yeah, but I mean, anything has a definition, right? Otherwise, it would have a name. Some math book somewhere has a definition for an